Elias. Meme, what do you call those things? Memes? His time is up. So what we were doing last time is we just said the area between two curves is just the difference in the values of the function integrated between the two vertical lines that define the limit. So let's see if we had any problems left in this section that I haven't done already. Yeah, it's that one. We were doing that one. Did we? Yeah, we finished that. And let's see. Yeah. Okay, we'll do one more here. Then we'll move on to section 2. So this is similar kind of problem. Sketch the region bounded by the graphs of the functions. Find the area of the region. Find the points of intersection. These are, well, yeah, between negative pi over 2 and positive pi over 2, those may not be the points of intersection. That's just the area that we need to look for. So remember what we did last time is when we had two functions and we were trying to find the points of intersection, we just set the two function values equal to each other and solve for the values of x where that equality was valid. So you do the same thing here. There's probably an infinite number of intersections. We're just going to look for them in a limited range. So what you end up with here's our two functions. So we have the sine of x equals cosine 2x. Solve for x. So we got to do a little trig stuff. I didn't bring my book, so I might have to. Did anybody bring their book today? we can look it up online. So do you remember what we need to do first? We got the sine of x, cosine of 2x, right? So somehow we've got to make this x without just taking our eraser out or moving it. I know I've seen in the past somebody's factored out a 2. You can never factor out anything. The only way that you can change the argument of trig functions is by using a trig identity. So let's look it up online since I didn't bring your book and you didn't bring your book. So we'll just okay. Ooh, what's that? Okay. I'm just trying to figure out what that is going on there. The man's thoughts are going into his brain, which is then going to his eye, and his smell's coming into his nose from the burnt toast. Okay, well, we got to see what that is. Redrew the map of the brain. Okay, interesting. Okay, trig identities. Inverse. I should have looked at the table of contents here. So they're called double angle formulas. There we go. So what we have is the cosine of 2 theta. So we have to pick one of these, and we always pick the one that matches the trig function, the other trig function. So we have the sine of x. So we want to use the one that just involves the sine of x. So we're going to use 1 minus 2 sine squared theta. So that means that this equals 1 minus sine squared x. 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 1 minus sine s So now we just put everything on one side. So we'll get sine squared x plus sine x minus 1 equals 0. So what I've done is I've just moved this to the left-hand side. It becomes positive. This one was already positive, and that one becomes negative. And then you could factor it out, sine of x, and one's going to be plus, well, oh, there's a 2 somewhere here, isn't there? Otherwise, we're in trouble. I think I wrote my trig identity wrong. There we go, 2. Yeah. So this should be, yep. So this should be 2. So this should be 2. And so one of those has to be 2. And then we're trying to get a positive sign here, so we're going to put the positive 1 with this matching up with that, so that when we do the outer, we'll get plus 2 sine x, and then we'll get minus 1 sine x, which will give us plus 1 sine x. So if we set both of these equal to 0, we'll get 3 solutions, really, but probably 2 that are in the domain that we're interested in. So this one, you'll get the sine of x equals a half, and this one you'll get the sine of x equals negative 1. And x here is 3 pi over 2. If you remember the unit circle, the y coordinate is the sine, so the only place the y coordinate is negative 1 is down there, so that's outside the domain. So those don't count. And in the domain negative pi over 2 to positive pi over 2, you're going to have, so we're just going to use the unit circle here. So the sine is the y coordinate. So I take a line at a half, and then I can draw my angle here, and the same thing. Now I'm wondering about this, because where sine is a half is over here, which is actually from 0 to pi. So I might have to plot this. I may have written something wrong down. Anyway, that's pi over 6. Remember, so one answer is pi over 6, and the other answer would be pi minus pi over 6, which would be 5 pi over 6. Let's just plot these two things, sine x, cosine 2x. And so that is a point of intersection, and that's a point of intersection. So that's the pi over 6 part. This looks like negative pi over 2, which I thought it was, so I'm not sure. Let me go back here and see did I do something wrong? Okay, pi over 6. I know that's the point I want. Why is it not working? Think about this. Oh, it's because it's this solution. Okay, yeah, that makes sense. Okay, so actually I was wrong here. This is true, but it's also equal to negative pi over 2. So 3 pi over 2 is the same as negative pi over 2. So that's one of the solutions, and this is the other solution, and this solution is outside the domain. Okay, I was just thinking it wrong. So these are the two intersection points. So which agrees with what we got from the graph. So all we have to do now is we have to integrate from negative pi over 2 to positive pi over 6, which are the limits where they intersected, and we have to figure out which one's on top. So the blue curve is on top, which is the cosine of 2x, so, or 2 theta. So we're going to take the cosine of 2x, and I'm going to subtract the sine of x multiplied by dx. So again, they didn't tell us what the limits were. They told us where to look. So we set the two functions equal to each other. Use the trig identity to get it all in terms of the sine of x. Factored it. As you can see, as you saw in the graph, there are an infinite number of solutions. The two that are in the domain that we specified are negative pi over 2 and pi over 6. So those are the limits. We looked at the graph, found that this was the one that was above that. And so all we have to do now is just integrate and evaluate the integrals. And so the integral of the cosine of 2x is going to be equal to 1/2 the sine of 2x. And the integral of the sine of x is going to be equal to negative the cosine of x. So what I'm doing here is using u substitution. And when you integrate something, a trig function that has a constant multiplied by the variable, you divide by that constant when you integrate. And here, you just look that up. The integral of the sine is negative the cosine. Integral of the cosine is the sine. That's why that's, and then you evaluate that between negative pi over 2 and pi over 6. So let's plug the numbers in. So we'll get 1/2 the sine of 2 times pi over 6 minus the sine of 2 times negative pi over 2. So that's the first one evaluated. And then you've got a minus times a minus, so that's a plus. So you get the cosine at the upper limit, which is pi over 6, minus the cosine of negative pi over 2. So this is 2 pi over 6 is equal to pi over 3. So I could replace that with pi over 3. And this is negative pi. So again, going back to the unit circle here, we're going to, so the sine of pi over 3, if you come over to the y-axis, this is going to be square root of 3 over 2. So we're going to have 1/2 times the square root of 3 over 2 minus the sine of negative pi. So negative pi is over here. Well, negative pi is this way, which is the y-coordinate there is 0. And then we have the cosine of pi over 6, which pi over 6 goes here. The cosine is the x-coordinate, so that one is also going to be the square root of 3 over 2. And here we have the cosine of negative pi over 2, which comes down there. The cosine is the x-coordinate, and the x-coordinate at this point is 0, so we get 0. So you get 1/2 plus 1, that gives you 3/2. Square root of 3 is your answer. So that's the area between those two curves. And thus, just to double check that I didn't make any mistakes, I'm just going to go online and do this. Use some. So let's see here. Online definite integral calculator. Okay, so we're integrating from negative, pi, forgot the negative sign, negative pi over 2 to pi divided by 6 of the cosine of 2x minus the sine of x. So that looks about right. Say go. And they say the answer is 1.29904. So let me get my calculator out, figure out what my answer is in terms of the decimal. So the answer was 3/2 times the square root of 3, which is, what did I get here? The wrong answer. Okay. Oh, here it is. Square root of 3 times 3 over, so it's close. 3/4. So what did I do wrong? Oh, yeah, right. Yeah, I forgot to multiply this part correctly. Sorry. Yep. I was missing something. So what we have here is you have the square root of 3 over 4 plus the square root of 3 over 2, which is 3 square root of 3 over 4, which is the right answer. Yeah, forgot to multiply by 1/2, or I did. I don't know what I did. Oh, I just forgot the 1/2 completely. Okay, so that's it for this section. I already gave you the homework assignment. Save that. Okay, so now we're starting the long trek through the next 2 sections. Like I said, we're going to spend a lot of time in class working problems out. So we knew in chapter 4 that the purpose of the definite integral was to calculate areas. That was the whole idea. What we just did there was said that we can look at areas that are not bounded by the x-axis and also do those, which was just a simple subtraction. What we're going to do now is look at 2 ways of calculating the volume of 3-dimensional figures. Now it's limited because we're dealing with single integrals. It's going to be limited to objects that have what we would call symmetry. I guess we call it symmetry around an axis. It's kind of like my thermos here, except that it doesn't have this plastic thing here. If it was completely the same, no matter how I rotated this thing around in terms of the shape of it, then I could figure out the volume of this container using what we're learning in the next week or 2. How many people know what a lathe is? Okay, a few people. So, yeah, go ahead, Daniel. Yeah, so there are a number of tools that you can use for shaping materials. Lathes used to be used for shaping. I mean, back a couple hundred years ago, like you had a chair leg or a table leg that's symmetric. You take a square piece of wood, and then you kind of rough cut it so that it was maybe somewhat circular, and then you would attach this thing called a lathe, and it would spin it around the center axis of the sort of circular thing. And then you would take a chisel, and you would set it up, and you kind of hold it up against a support. So you'd hold the chisel up against the wood, not just freehand, but you'd have some kind of support-ish thing. And you would move it along, and then as you moved it in and out, you'd create a pattern on the leg. So that was, and then when you came to making things out of metal, like guns, or anything that's circular that's made out of metal, you would use a lathe. Now the other things that people will use, if you had a piece of metal and you want to just cut it, you'd use a saw, usually a band saw or a reciprocating band saw. It's like a what do you call those things? The kind of saws that you cut metal with. Just go hacksaw. Yeah. So it's kind of like a hacksaw, but it's a motorized hacksaw. And then the other thing that they use is what's called a what's it called? Milling machine. How about a milling machine? Daniel, you know what a milling machine is? Milling machine? Yeah. So milling, I'll just show you here. I mean, you used to you'd have a drill to make holes. So it's kind of like a drill, but it's also kind of like a router, but it's for metal rather than wood. Let me just show you a picture here. And we'll do images. Milling machine. So these are lathes. It's not a milling machine. But that's what a lathe looks like. You clamp. Let me see if I can. I can't zoom in, I don't think. Yeah, well, I can. So the way the lathe works is you clamp the metal piece in here. And this is where you would put the tool, which is just a sharp piece of really hard, sharp metal. You clamp it in this thing right here. And then you use this part, you move it close enough so that the metal circular thing is clamped here and also supported here, and then you spin it. And while you're spinning it, you cut it with the hardened steel tool. They call it a tool. Okay, so that's what a lathe looks like. Now, this is what a milling machine looks like, or at least one kind of milling machine. So let me zoom in a little bit on that thing. Now, the way a milling machine works is you still have it's kind of like a drill bit. It's like a drill press. I haven't used these words for a long time. I have to dig deep into my memory. A drill press is you have a thing where it has like a handle, and you want to drill a hole through some material. You take the handle, and it by leverage pushes the drill onto the surface and provides force, so that then as it's turning, it will drill the hole. What a milling machine is, you clamp a tool that kind of looks like a router bit, and then you clamp your piece of metal that you're trying to machine onto this flat surface. And this flat surface can move both this way and this way. So it has two controls. It's kind of like a 3D print. 3D printers, actually those stay stationary in the jet moves, I guess, but it's the same concept. In this case, you're clamping the metal on this very substantial platform, and then you keep this stationary, and then you move the piece to cut out the material into the shapes that you need. So anyway, That's my manufacturing mini course there. Okay. So what we're going to do is we're going to look at things that you could make on a lathe, but they, as I said, they are circularly symmetric. So the kind of the simplest example of a circular symmetric shape is you basically take a rectangle. So this is a rectangle, and you rotate it around some axis, which is at the center of, at the bottom of this rectangle. And this rectangle, as it's rotated around, sweeps out an area and creates a disc. Because you can think of a disc two ways. You can think of a disc as a circle and moved like this, and that would create a disc shape. Or the other way to do it is to take a rectangular shape like this, okay, so it has two dimensions, and then you rotate it around one side, one part of the sheet. So it would rotate around like this, and it would, as it rotates around, it would create the same shape as if I took a circle and pushed it this way. So if we look at the area of the rectangle that I'm rotating around the one side of the rectangle, around this axis, the area of the rectangle is just the width of the rectangle times the height of the rectangle. In terms of this disc, it's the width of the disc. So as I rotate this thing around, the width of the disc that I'm creating is equal to the width of the paper, this dimension. And the radius of the disc is this dimension of the paper. So it rotates around like that. Okay. So you can see in my drawing, I've got this W and I've got this R, which is the distance, basically this distance of the rectangle. So the dimension is a rectangle, W by R. And the volume of the disk results is equal to pi r squared times W. So that's actually more associated with if I did it the other way, where I take a circle, which is the area of a circle is pi r squared, and I move it perpendicular to the disk. That's the W part. So there's two ways of creating it. You can do the rectangle around that way, or you can make the circle go this way. And either way, it's going to be pi r squared W. So the whole concept of finding the volume of something other than just a simple disc shape, something that has some contour to it, like this, is you take the equation that would define the curve. If I were to project this into two dimensions like this, and I just drew around it, it's going to be a two-dimensional object, the shadow. I can't take it away. Stay there, shadow. It won't stay there. So hopefully you can see the shadow. So that's the two-dimensional shape. And what actually I would do is I take it, the two-dimensional shape that's cut right down the middle, and if I rotate that around the axis in this direction, it's going to create this, which I'm trying to figure out the volume. So if I take this and I make each little segment into a rectangle, all I have to do is add up all the little rectangles, and I get in case of finite width rectangles, I get an approximation to the volume of this object. But if I make the number of rectangles go to infinity, or the number of disks to go to infinity, then I get the exact volume of this object. So when you sum up a bunch of little rectangles, that's integrating. So when we do this with disks, we get a volume instead. Okay, there's my lathe. And here's some pictures. Well, this is actually just, I have a software on my computer, which I'm trying to find the Yeah, so let me go back in here. So what I have here is just a sequence of pictures, which this one is the two-dimensional side view, which has it's defined by the x-axis, the y-axis up to a certain point, and then it has this function, however that's defined, till you get to over here, and then you have another vertical line. What this thing is, you'll see in a second what that is. That's what I'm going to rotate this two-dimensional object around. The axis is this red line, and the red line is perpendicular to this circle. So you basically drag that thing around in a circle around this circle to create the three-dimensional figure. And that's what we see in the next picture, is this two-dimensional object becomes this three-dimensional object. So let's see if this is going to work or not. Yes, that's the question. I think they reconfigured my computer, and I don't have it on. I've forgotten that I don't have it on here, so I may not be able to do that today, but I'll get them to put it on there. Yeah, let's. Yep. Okay. I'm just going to show you where it is. If you go to, it's called SketchUp. Let's see if that works or not. There we go, SketchUp. And I'm just going to I guess I can't get it and install it on my computer, but it was developed by Google, and it's one of Google's apps. You can use the free version, or you can, if you're doing some professional stuff, you can do you can buy the better version. So here's just some examples. We're not going to get this complicated, but I guess these actually were made on SketchUp, which is pretty impressive. Even my daughter, who's in architecture, knows about SketchUp. So once I get that working, we'll show you how it works. So we can't do that today. And here's some other examples of some symmetric things, all dangerous. Bullets, cruise missiles. Okay, so here's the math. So what we're going to do is we're going to say that each one of those little disks is a small volume. We're going to call it dV, V for volume. The I is the subscript. So as you stack up all those disks, each one's going to have a volume. The first one is the one on the left. The second one is the next one, all the way to N. And using the formula for the volume of a disk, it's going to be it's going to be pi times r squared, which is the area of the circle, times the width of the disk. In this case, instead of being W, it's just dx, which is the differential. It just means it's a really small thing. So the total volume is we just add all those disks together. So how do we represent addition? Well, we have the summation sign from I equals 1 to n of pi times r squared, the local radius, times the dx value. And then to get the exact value, we take the limit as the number of rectangles or the number of disks goes to infinity. So the total volume here, the exact answer is the limit as n goes to infinity of the summation from I equals 1 to n of pi r squared times dx sub I. Well, that is the integral. So if we, I think the next page. So for the disk method, because that's what we're doing, is we're making all these disks to make all these small disks to make a continuously changing cross section, is equal to the integral from a to b, which are the x limits of the two-dimensional object times pi times this radius value, which is a function of x, squared times dx. So instead of the integral of f of x dx, it's going to be equal to the integral of pi times this radius function squared times dx. So it's not that much more complicated. So we're going to do a simple example here first. What we're going to do is we're going to take this triangle, which originates here at the origin, goes up at a 45-degree angle, and we're going to go until x equals 3, so y would equal 3, and we're going to rotate that around the x-axis, and we're going to create a cone. So this will be the tip of the cone, and this side will be the base of the cone. And in these calculations, you want to draw the figure, so you want to do a rough sketch of whatever the function looks like. We usually also include this little rectangle, and what this is doing is it's kind of to give us to guide us through the process of setting everything up. Because the things we're going to have to figure out is what is this radius function, what are the limits, and in this case we are integrating. We're going to integrate with respect to x. So you can also, we'll find later that you can not only rotate around the x-axis, but I could rotate around the y-axis as well, and that would give me a totally different answer. And so if I'm rotating around the y-axis, I may have the rectangle rotated this way. So the direction of this rectangle relative to the thing that I'm rotating around is going to help make my decision-making process better. This little arrow is just telling me that I'm rotating around this line. If I was rotating around this line, I'd put a little arrow. So it's a curved arrow to show that it's rotating one way or the other. Okay, so that's my drawing. So the question, the way we would ask this question is, what is the volume of the area bounded by y equals x, the x-axis from x equals 0 to x equals 3 when rotated around the x-axis, question mark. So what it's saying is we're going to take the area bounded by this curve by the value x equals 3 and the x-axis. So this terminology describes what this area looks like. And then I ask what is the volume if this thing is rotated around the x-axis. If I said around the y-axis, then I'd have to do a different problem. But in this case, that's what I'm looking at. So you have to determine what r of x is. And r of x in this case is equal to x. Because that's the curve, the red curve, it's what is defining the upper value of this rectangle, the height dimension of the rectangle. So this r of x is usually whatever this curve is that's defining the outer bounds of the outside of the three-dimensional object. So, this is like y equals f of x, but it's really r of x because I'm talking about a distance. Okay, so that's r of x. A equals 0, which is the leftmost part of this figure, and b equals 3, which is the vertical line that defines that part. So to find the volume of this cone, all you have to do is take the integral from 0 to 3 of pi times x squared times dx. I put it in parentheses because I wanted you to, if you look at the formula here, it's got r of x in brackets. So I just wanted to emphasize that this is the radius and I'm squaring it, even though effectively you're just squaring x anyway. So now all we have to do is just a simple integral. We take pi outside the integral sign, so we take the integral from 0 to 3 of x squared dx. So the integral of x squared dx is x cubed over 3. We evaluate that between 0 and 3. And so that's going to be equal to pi times 3 cubed over 3 minus 0 cubed over 3. And 3 cubed divided by 3 is 3 squared, so you just get 9 pi. So that's the volume. I don't have any units, but if we had units, it would be units cubed. And that makes sense because x has dimensions of length. So if we cube that, we're going to have cubed units. Now we'll go online here for just a second. So we'll say equation for volume of cone. So there you see, this is basically what we generated. The triangle is this part. So you go up to here, over there, down there. And if you rotate that triangle around this vertical axis, you create a cone. And if you look at the volume, it's equal to pi r squared h over 3. So you can see where the 3 comes from. Because when we integrated x squared, we got x cubed over 3. The pi comes from because we're dealing with something that's a circular symmetric kind of thing. And I could have worked this problem out. Instead of going from 0 to 3, I could go from 0 to h. Actually, let's just do that. So let's generalize it. Let's derive this equation, which you've seen before. So let me just, what I'm going to do is I'm just going to do the same thing we had here, except this is h of the cone. So instead of integrating from 0 to 3, I'm going to integrate from 0 to h. And this is r. So that's the radius. That's the radius of the big part of the, the bottom of the cone. So what you would end up with is, in this case, you'd have pi times the integral from 0 to h. But there's this relationship between h and r. What is it? Oh, yeah. So this, if you look at the equation of this line here, it's y equals, this is the slope. The slope of this line is going to be equal to rise over run times x. Okay, so that's the value of the function. It's not just a 45-degree line. It depends upon the ratio of r and h. So instead of having x squared here, we're going to have r over h times x squared dx. Okay. So that's the difference. Here, as ours was a 45-degree angle, here it depends upon the ratio there. Okay, so we get pi times, these are constants for a particular cone, so I can bring those outside the integral. So you'll have r squared over h squared, and then you'll have the integral from 0 to h of x squared dx. So then we integrate this. and we'll get x cubed over 3 integrated from 0 to h. Then you plug the limits in, so you'll have pi r squared over h squared times h cubed over 3 minus 0 cubed over 3. And you can see these cancel out with 2 of those, so you're left with pi r squared h over 3. Ta-da! I haven't done that before. And you get the answer. Okay. So that's how you use calculus to come up with the expression for the volume of a cone. You just took it for granted that's what it was, but now you know why there's a 3 in there. Okay. So the formula we just used was this one. This is if you're rotating around the x-axis. So the volume is pi times the integral from a to b of r of x squared. In this case, they factored out the pi, which is a constant. But you can also rotate around the y-axis, and the formula looks like that. So the volume is pi times the integral from c to d of r of y squared dy. And the limits are the y limits. So when you integrate, when you use the disk method around the y-axis, the bounds have to be a function of y instead of a function of x. And we're not used to thinking that way. That's why we have to spend so much time. One of the reasons we have to spend so much time on this particular section is it's just a little bit beyond what we think. So let me just explain what that means. So, back to algebra, or I guess it's algebra. No, maybe I don't know which one it is. Okay. You remember we said you've got a function. Has one y value for every x value. And we use the vertical line test. If you have a relationship that when you draw a vertical line, you have more than one intersection with that line, with that curve, then we would say it's not a function. But the reality is we should add the extra qualifier. The vertical line test is to tell us whether something is a function of x. So if I have something that's a function of y, using the word function, then what it may look like. Well, let me just give an example here. This is something that we plot all the time. Well, we don't. This actually is a function. So, but if I had something that looked like this, so instead of a parabola going up, it's going to the side. If I drew a vertical line, I'd say that this was not a function. But really, this is not a function of x. Because if I take that same relationship and do it down here, and instead of using a vertical line, if I used a horizontal line, then with a horizontal line, it only intersects one place. So the way I would say this is this curve is not a function of x, but is a function of y. And the function would be something like x equals y squared. So everything gets turned around. We're so used to thinking of y equals x squared, y equals something, as a function. But that's a function of x. But we can equally flip it the other way around and say x equals y squared, which is what this is. And this is a function of y. So instead of saying up here for a parabola this way, we'd say f of x equals x squared. The way that we do this down here is we'd say f of y equals y squared. So f of y is the same as x, just like f of x is the same as y. And that's what we're doing here. We're going to rotate around the y-axis, and therefore we don't write this, we use this function. The x is a function of y instead of the y is a function of x would be equal to the square root of x and minus the square root of x. That's the way you would have to represent that thing as two parts. Okay, we're oh yeah. So this is looking at two problems, depending upon whether we rotate the curve around the x-axis or the y-axis. So what I have is a parabola. And we would think, oh, that's a parabola. The equation is y equals x squared, which is true. The x limits would be from 0 to 3. And so to find the area, the volume associated with the blue area, so what I'm doing is I'm going to rotate this curve around the x-axis. So it ends up being like a cone, but with a curve to the cone. You know, instead of being a flat cone, it's going to have a curved side to it. I'm not sure what. Is there anything that I can think of that has that shape? It's kind of like half a tornado or something like that. You know, it has a curvature to it instead of just being straight. So to find the area created by this curve, this vertical line, rotated around the x-axis, going like that, you'd use this equation. The equation that's defining the radius is y equals x squared. So that's r of x. And we square that. So we take r of x squared. We integrate from 0 to 3 times pi. That'll give us the volume. So let's just go ahead and, while we're at it, let's calculate that. Well, we only got 5 minutes left, so I'm going to one more point. So if you, though, instead of rotating around this way, if you rotated this curve around the y-axis, instead of having something look like that, it would be kind of, it's kind of like what's a good, it's like a little mound of something, except upside down. Okay, like a ball. Yeah, right. So it's kind of like a ball that was filled with something. So it's a ball that's completely, it's not empty, but it's full to the brim. That's what it would look like. And in that case, the way you would do the calculation is, first you have to take the function that defines, or the line that defines this boundary, and instead of being y equals x squared, you solve for x. So to do that, we just take the square root of both sides, and you get x equals the square root of y. So that's this curve as a function of y. Here, that's the same curve as a function of x. So instead of r of x being x squared, it's going to be equal to the square root of y. So that's the radius. That's the function. So that's the distance from here to there instead of the distance from there to there. So that's the radius, and then you square it because you're dealing with a circle, pi r squared. You integrate with respect to y, and instead of the limits being from 0 to 3, they're from 0 to 9 because it's the y limits associated with that. And if you looked at, which one do you think would be bigger? You would think the red one would be, just because of the way it's curved. Either one of those is not that hard. This we'd have x to the 4th. We'd end up with x to the 5th over 5. There, you square the square root of y, you'd have y. So you'd integrate y, which would be y over 2. and then you plug the numbers in. So we'll see on Monday. We'll do both of the integrals, see what the values are. Hopefully I'll get SketchUp on, I can show you.